Hello and welcome back. In our last video, we spoke about the 8086 bus timing diagrams, specifically in the minimum mode. Today, I'm going to talk about the design of the 8086 instruction set. And I'm not going to go into every single instruction, there are just too many of them. It's not necessary, you can read up about them. But I'm going to talk about the design of the instruction set. I'm going to talk about a couple of examples of the more complex ones so that you begin to get an understanding of them. Alright, so what are the kinds of operations that you can perform inside a processor or with the processor? Right? So one is, of course, you can move data within the ALU itself, the arithmetic logic units, right? So you're going to read and write additions, etc. All of those happen within the ALU. That's something that you need to do. You can also move data between the ALU and the input-output ports. You can move it between the ALU and the various registers that you have. You can move it between the ALU and the external memory. So data can be in or out from the external memory. On top of that, the registers can talk to each other. So AX can move to BX, BX can move to CX, so on and so forth. So there is data movement amongst the registers themselves. And all of these kinds of movements is enabled by the instruction set of the 8086. There are basically two terms for something called the addressing mode. And the addressing mode is something that's important to understand when you talk about instruction sets. The first definition really is the way an operand is specified within the instruction. So there can be immediate operands, there can be indirect operands, so on and so forth. That is one definition of the addressing mode. The other definition of the term addressing mode is the way to access variables, arrays, records, pointers, and other complex data types. So these two are standard accepted definitions of the term addressing mode, and addressing mode is important when you want to understand the instruction set of any processor. So let's look at the different kinds of addressing possible in 8086. There are four major families of addressing modes. One is the immediate addressing, register addressing, there is memory addressing, and there is I/O addressing. So these are the four big types of addressing modes specific to the 8086. The memory addressing in turn has direct memory addressing and indirect memory addressing. The indirect memory addressing has 5 different subsets. The input-output addressing, the I/O addressing, has a fixed port addressing mode or a variable port addressing mode. So what this really gives you as a programmer is 1, 2, 3, 4, 5 plus 5, 10 different addressing modes for accessing information, I/O ports, memory locations, etc. in the 8086. Let's break up a typical instruction. So the instruction consists of a label, and it's optional. You don't have to have it for every instruction. In the example of start, move BL, 22H, the label is the word start, and this is a label that is used during the assembly process. The operation code is mandatory. You cannot have an instruction without the operation code. And in this case, it is move BL, The operand is mandatory in some instructions. It's not mandatory in others because it is implied in some of the instructions. In this case, it is the value 22H, semicolon. So this is the complete instruction. On top of this, you have something called a comment. And the comment is optional. The comment is used to help the reader of the program understand the program better. In this example, the comment says moves or copies the immediate data 22H into the register BL. So this is the breakup of a typical assembly language instruction. Now when you look at the instruction set of the 8086, you should be able to identify these 4 components in most of the cases. There are 9 different kinds of assembly language instruction categories, and I'm not going to go into all of them. There's data transfer, there is arithmetic instructions, logical instructions, shift and rotate instructions, so on and so forth. I'm going to explain a couple of them, just the more complex ones. So let's look at the instruction called XLAT, and this instruction is really a data transfer instruction, translate. XLAT stands for translate. What this instruction does is really look into a lookup table and take out the value at a specific memory location. How is this done? So let's assume that the data segment points to a certain location in memory, and The BX register points to the start of the lookup table, the bottom of the lookup table. And that lookup table is obviously within the data segment. The AL register then points to an offset within the lookup table. So in this case, the offset can be a value from 0 to 255 because it's an 8-bit register. The AL is an 8-bit register. So the lookup table can be a maximum size of 255 bytes starting at the location pointed by BX. So at the end of the XL80 instruction, the value, so first of all, the offset is calculated by BX plus AL. So the value in AL is added to BX to look at the offset within the lookup table. The value in that offset location, which is in this case 3FH, is then moved back into the AL register. So this gives you one instruction to perform such a complex operation. This is called the translate instruction. Another nice instruction, very useful instruction, is called the shift operation. And there are various kinds of shift. There is a logical shift. The logical shift moves bit 7, the highest bit, B7, into the carry. The carry flag is now the bit 7. Bit 0 of the value is filled with zeros. So B0 becomes 0. B7 moves into, is shifted into the carry flag. And you can use this to determine what the bit 7 of every byte in memory location is, if your program so decided. The arithmetic shift is a little different. So the arithmetic shift from the bit 7 moves to the carry flag. So that part is the same. But bit 0 is not filled by the value 0. It just repeats itself. If you therefore did 8 such shift operations, arithmetic shift operations, all the 8 bits would be what the value of bit 0 was initially. And you can just kind of think about it, you will understand that quite easily. So how does the shift operation really work? I mean, what happens within the processor? Right, so the two things that are important for the shift operation: what will get shifted and how many times will it get shifted by, right? So the instruction itself will tell you what gets shifted and by how much. So how does this work? What can get shifted is really a value in a register. So and you can choose what register that is, and you can say, look, I want that particular value to be shifted right or shifted left, arithmetic right or a logical right, whichever way you want to do that. The other one is you can give an immediate value. So a 8-bit value can be shifted right or right, and that 8 bits can be in memory. It could be a word, it could be 16 bits long, or it could be a double word, 32 bits long, again in memory. So you can shift left or right, arithmetic or logical. You can shift something in memory, you can shift something in a register. How many times can you shift? It's not just one shift. So if there is no instruction, there is a default condition is 1, so it will shift by 1 bit. But it can also shift by the value in the CL register. So if you load the CL register with the value 4, it will do a shift by 4, either a left or a right, arithmetic or a logical, it will shift it by 4. It can also shift it by a specific number if you define that number. So this is the way this particular instruction works. Let's now move to another fairly complex instruction called the rotate instruction. The rotate instruction, as the word presumes, must rotate something. And in this case, bit 7 gets rotated back into bit 0. And bit 7 also gets copied into the carry flag. So what you can do is you can inquire from the carry flag what was bit 7 of a specific memory location, etc., just by using this instruction, and you don't lose the value because it gets copied back to bit 0. This is rotate without carry. The other option is to rotate through carry, in which case bit 7 goes to carry flag, and whatever was in the carry flag comes back to bit 0. You'll see that's pretty obvious. The difference between the two modes, rotate without carry and rotate with carry, the difference is pretty obvious from this diagram. So in this video, we spoke about the design of the 8086 instruction set. We spoke about a couple of examples that translate the rotate and the shift instructions. just to give you a feel for what these kinds of instructions are. And as I said, I'm not going to go into the details of every single instruction that is present in the 8086 family. However, in our next video, what I will do is talk about string operations. Fairly complex operations. You can do a lot of things using strings. I'm going to be talking about how to use string operations effectively. In the meantime, I would urge you to start looking up and reading through all the instructions of the 8086. Try to understand the way these 8086 instructions are crafted, and I'm sure there is enough material out there in case you have a doubt. Have fun reading, and all the best. Thank you.